Hello and Assalamualaikum everyone. We are from Physics 370. We present about wave, motion and sounds for our multimedia assignment. First of all, let me introduce my group member. First, we have Muhammad Firdaus bin Ilyas, Ahmad Izzat Iqbal bin Zaini, Nur Suhaila binti Muhammad Safari and me, Nohani Sohana binti Ramlan. Next, I will pass the mic to Ahmad Izzat to start our presentation.
Wave motion is deviation from a state of rest or equilibrium from place to place in a regular and organized way. The common example of wave motion is the wave on water surface. Both of sound and light travel as wave-like disturbance, and the motion of all subatomic particles exhibit wave-like properties.
Good morning and good afternoon. My name is Nur Suhaila binti Muhammad Safari and a student in your Physics 370. Thank you for giving me the opportunities to present to you today. I have prepared a presentation on wave motion and also sound that we've covered in our course. It concludes key points such as sound and ultrasound, generation of ultrasound wave, receiving ultrasound, ultrasound scanning modes, and prop of transducer selection. I greatly value your feedbacks and insight, as they will help me grow as a student. I appreciate your time and support. Let's begin the presentation. Thank you. The human ear is an organ capable of detecting sound as a vibration transmit through a medium. However, there are limitations to the range of frequency we can perceive. Frequency below 20 Hz, known as infrasound, are not audible to the human ear. On the other end of the spectrum, ultrasound refers to frequency beyond 20,000 Hz that are also beyond our hearing range. Ultrasound is defined as a sound with a frequency exceeding 20,000 cycles per second. In medical diagnostic, higher frequencies in the range of millions of cycles per second are utilized for specific diagnostic purpose. An ultrasonic beam refers to a focused stream on high-frequency sound wave. In ultrasonography, the technique used in the medical imaging, the principle of reflection and refraction are applied to analyze the aqueous product by the interaction of the ultrasonic beam with tissue and structure in the body. These provide valuable information for diagnostic purpose. Small objects or structure have the ability to reflect ultrasonic energy and allow them to be detected by the visualized during ultrasound examination. These properties enable the detection of various anatomical features and abnormalities within the body. One important aspect to note is that ultrasound as a diagnostic tool is considered safe and non-invasive. It does not pose any harm to health as it utilizes sound wave instead of ionizing radiation, which is used in some other imaging techniques. This makes ultrasound widely used and preferred imaging modality in medical practice due to its safety and real-time imaging capabilities. When it comes to ultrasound imaging, a gaseous medium such as air can interfere with the propagation of ultrasound energy. To overcome this limitation, it is important to ensure that ultrasound transducers have direct contact with the body. Without any air gaps, this airless contact facilitates the transmission of ultrasound wave and improves the quality of the imaging result. In the term of image quality, ultrasound does have certain characteristics that differentiate it from X-ray and magnetic resonance modalities, which is MR. Ultrasound image can appear somewhat noisy and may have lower contrast compared to X-ray and MR image. This is primarily due to the way ultrasound works, as it relies on sound wave reflection and echoes to create image. The noise and lower contrast can be influenced by various factors such as tissue density, ultrasound setting, and the presence of artifacts. However, the advancement in the technology and image processing technique continue to improve the quality and clarity of ultrasound image, allowing for better visualization of anatomical structure and abnormalities. Sound waves are formed when the molecules in the medium vibrate together. A sinusoidal sound wave consists of compression and rarefaction zones. The peak represents the highest pressure and the nadir represents the lowest pressure. One circle includes a compression and a rarefaction, while the wavelength in the distance between two consecutive peaks or valleys. Now, let's move on to the next slide, where we will explore generation of ultrasound wave. The development of compact piezoelectric crystal transducer revolutionized the field of ultrasonography, enabling it to become a viable medical imaging modality. The term of piezo, derived from pressure, indicate that piezoelectric crystals generate pressure or mechanical vibration when electrical energy is applied to them. These unique properties allow this crystal to convert electrical signals into sound waves, making them essential components in the ultrasound technology. When a piezoelectric crystal is subject to high frequency sinusoidal electrical stimulation, it undergoes expansion and contraction, resulting in the generation of compression and rarefaction. This change in the crystal shape produce corresponding sound wave. The high frequency electrical stimulation cause the crystal to vibrate, and also it create a sinusoidal vibration pattern, and this is a vibration that transmit through a conducting medium such as human tissue during the ultrasound imaging. As the sound wave propagate through the conducting medium, they interact with the tissue and generate echoes that are captured and also analyzed to produce diagnostic image. And that's all for my part. Next, I pass the presentation to the next presenter.
I will continue to present about receiving ultrasounds. Piezoelectric crystals have another very useful property that enable it to be also used for receiving ultrasound wave. When a piezoelectric crystal is compressed, it generates a voltage. This property is used to listen for the ultrasound wave that return after striking objects. When returning sound wave hit the piezoelectric crystal, it gets compressed. The crystal then generates a voltage that corresponds to the intensity of the ultrasound wave that hits it. The ultrasound machine conveniently uses the same piezoelectric crystal to transmit and to listen to ultrasound wave. First, the machine applies a voltage to the crystal to expand it and transmit. The ultrasound machine then very quickly switches to a listening mode by monitoring the voltage across the piezoelectric crystal. This transmit and receive cycle is repeated very rapidly. The examples show only one crystal for clarity. In reality, ultrasound probes are composed of a large number of individual piezoelectric crystals. The information gathered from the crystals are processed by a computer to display the image on the screen. Once the ultrasound enters the body, some of it returns back to the probe to help the machine form an image, and the rest is lost. When ultrasound enters the body, some of it undergoes attenuation, refraction, and reflection. What is attenuation? When the ultrasound waves are attenuated, that is when the body absorbs the ultrasound energy, making the wave disappear. These waves don't return to the probe and are therefore wasted. The more the body tissues that the ultrasound wave has to cross, the more attenuation the wave suffers. That is one reason why it is more difficult to image deeper structure. Next, refraction. Every substance, such as nerve, muscle, or fat, has a unique property called acoustic impedance. Acoustic impedance basically depends on the density of the substance and the speed of ultrasound in the substance. And substance with different acoustic impedance alter the course of ultrasound wave in an important manner. And lastly, refraction and reflection. I will show you the figure that show what happens when an ultrasound wave tries to pass from one substance to another substance with a different acoustic impedance on the next slides. The red arrow is the ultrasound wave. Part of the ultrasound wave continues into the second substance but becomes slightly bent away from the original direction. Look at the pink arrow. It bent. Part of the wave, the blue arrow, is reflected back to the probe. The amount reflected back depends on the difference of the acoustic impedance between the two substances. More the difference, more the reflection. Only this wave can return back to the probe and provide information for the machine to show image. As the ultrasound wave cross from one tissue to the next, each with different acoustic impedance, some of the wave is reflected back at each crossing. Look at the two blue arrows.
Introduction to ultrasound scanning mode. Ultrasound scanning is a non-invasive medical imaging technique that uses high-frequency sounds waves to produce real-time image of the body internal structure. Ultrasound scans are commonly used for diagnosis purposes in various medical fields, including abstract cardiology and radiology. Principle of ultrasound scanning. Ultrasound scanning works on the principle of sound wave reflection and echoes. A transducer is used to emit high-frequency sound waves into the body, which then bounce back and adjust the encounter different tissue or structure. The transducer also acts as the chief, capturing the echoes and converting into electrical signal. Type of ultrasound scanning mode. B mode, brightness mode. The most commonly used ultrasound scanning mode. B mode produces a 2D scale image of the scan area, providing detailed anatomical information. Doppler mode. Doppler ultrasound measures the velocity and direction of the blood flow in vessel, helping to diagnose conditions such as blood clot, artery stenosis, or valvular abnormalities. Motion mode. Motion mode displays movement over time by scanning a single line repeatedly, allowing assessment of cardiac motion or fetal heart activity. Advantage of ultrasound scanning. Non-invasive. Ultrasound scanning does not involve radiation exposure or surgical procedure, making it safe and preferred imaging modality, especially for pregnant women and children. Real-time imaging. Ultrasound scan provide immediate visual feedback, allowing healthcare professionals to observe dynamic processes such as blood flow, organ movement, and fetal development in real time. Portable and cost-effective. Ultrasound machines are relatively compact and portable, making them easily accessible in various healthcare settings. They are also generally more cost-effective compared to the other imaging modalities. Application of ultrasound scanning. Obstetric. Ultrasound, ultrasound scanning is widely used in prenatal care to monitor fetal development, detect abnormalities, and determine the baby position before delivery. Cardiology. Ultrasounds can help assess heart function, visualize the cardiac structure, and diagnose conditions like heart valve disease or abnormalities in blood flow. Radiology. Ultrasound is used to examine abdominal organ, example liver, kidney, gut, bladder, diagnosis condition in the pelvic area, the uterus, ovaries, prostate, and gut needle biopsies or fluid aspiration.
The last topic is selection of probe. Generally, the differentiation type of probe is described by the size and shape of their face. Using the right probe, for example in examining the patient, is important to get the good image. There are three types of probe that cover in this syllabus, which is straight linear probe, curvilinear probe, and phase probe. Straight linear array probe is designed for superficial imaging. The image that produced from the straight linear array probe is in rectangular shape. This probe has higher frequency than other probes, which in range 5 to 30 MHz, that provide better resolution and less penetration. The crystals are aligned in a linear fashion within a flat head and produce sound wave in a straight line. This image is example of straight linear array probe image in rectangular shape. The point R in this image is represent of rib, S is shadow of rib, and P is a plural line. The curvilinear array probe will produce image in sector shape. This probe has range of frequency between 1 to 8 MHz. The crystals are aligned along a curved surface and cause a fanning out of the beam, which result in a field of view that is wider than the probe footprint. This probe usually used in scanning deeper structure, which is organ. The example using of probe is used in abdominal and pelvic application and musculoskeletal evaluation or procedure which is in obesity patient. The last type of array probe is phase. This probe will produce image in sector type. It have crystals that are grouped closely together. This probe has frequency between 2 and 8 MHz, but usually it operates at the higher and making it ideal for echocardiography. The timing of the electrical pulse that are applied to the crystal varies and they are fired in an oscillating manner. This probe allows the user to maneuver more easily between the rib and small spaces. This picture is the one of the example that produced from the phase array probe. This picture is from cardiac image, which is the heart. RV in this picture is right ventricle, AO is represent aortic outflow, LV is represent left ventricle, LA is left atrium, and DA is descending aorta.
So as for conclusion, ultrasound is a type of imaging technique that use high frequency sound wave to capture image of the inside of the body. It can be used to visualize various organs, tissues and structure. Ultrasound can be applied to various parts of the body for diagnostic and monitoring purpose, depending on the specific medical needs of the patient. So that's all from us. Thank you for listening.